Thanks. The Kovács guy is back. Yeah, yesterday I was told that I'm stretching the definition of Tableau quite a bit when talking about string solving, so I'm sorry for that. This time I will talk about something that's definitely Tableau, but I will not use it as well in English before. So this is joint work with my supervisor Laura and with the lady guy over there, Michael. So just to motivate the thing a bit, so here we have a landscape of different boards, and in particular I'm talking here about two on the left-hand side. We have the wonderful, fancy, modern world of SAP, which is understood quite well. Everything is nice, everything is modern. Well, there's not much to do, it's easy. Whereas on the other side, we have mostly that properly. Unfortunately, which band of those, but everything in them is mostly very nice. Whereas it's easy. Well, the TBCL, we just hit it with well, mostly not really relevant which sets over the one mostly written by Amir. We got a result pretty easily. So just to motivate a bit, consider this very simple topology here. Well, if we want to prove it in set solving, it's fairly easy. We just transform it into a CNF. Oh, and get this here, we will apply full length constraint propagation, and you'll get it on it. So nice. But now let's take a bit more, let's say, interesting calculus like Hilbert calculus. Yes, that's not so nice anymore. I mean, I guess some of you will have hearts in their eyes when seeing it, but most people don't. They are rather screaming. They don't really want to do anything with it. So what we try is kind of to build a bridge between those two worlds and kind of create something like a proof object and then use set solving, or at least I use in set solving solution and certain category. And let's step one, or several steps back. Why do we actually care about them? Why do we want to combine them? Well, simple answers, set solvers are damn efficient. So when looking at the result from last couple of years, you see there's a huge increase in performance just over the last couple of years. And then get more efficient every year on Excel, at least for the next couple of years, it will go on. Okay. I come to the point, so far I didn't say anything really interesting for you. Mike and I wrote a paper at the workshop at TABLEAUX 2023, and we kind of conjectured, well, set solvers are an amazing way to kind of use this to solve certain categories, or to find proofs in certain categories. And well, we're just continuing on that end, and that's what I'm presenting to you. Okay, just a brief introduction. So I will talk in particular about the so-called first-order connection calculus, which is actually well established in a variation of Tableau. And yes, I mean, it was one of the first actually calculated for doing automated theorem proving. And yeah, I mean, it was introduced by a lot of different names. So people, for example, call it connection calculus, Loveland, I think, called it model elimination. There was also it's what called the system of matings and so on and so forth. But in the end, it's just a version of first order Tableau, effectively binary resolution, and it's yeah, sound complete. That's great. Super. So the group will find it eventually, maybe, if we're good enough. But unlike ordinary Tableau calculus, it's goal directed and non-confluent. Only non-confluent, I guess most of you don't know what it means, but for those who don't, it just means if you do a wrong step, you can end it in a dead end. So there isn't a proof anymore. We can't close certain branches just by making one wrong decision. Giving an example here, so using binary resolution to make it easier. If you have these four clauses here, two of them are units, and we just resolve A with, well, the first one, we end up with the B here, whereas we resolve with A here with the C, then we end it, I would say, not it, with this third clause, we already ended with C. And of course, with the C, we immediately get a conflict by resolving it with the negation of C, but if we get the B and we're required to do something with this B, well, then we get stuck. So yeah, so that's why most first-order connection calculus solvers, probably even all, I use some kind of iterative deepening and proof enumeration. That just means they just try out all possible proofs in the system. Maybe they're a bit more intelligent and just drop some cases, but most people what they do is just try out brute force, computer science. So far there's connection calculus, usually represented as a tableau. I will not do that here. Let's take a more fancy approach and just using the matrix representation, which will look a bit strange, but I will briefly introduce you to it. Just as usual, you have a three-variable tableau. In other words, we have eigenvariables. Whenever we have a universally quantified curve, well, we just copy it and do something with it. We just kind of instantiate it with the right elements. And then we just draw lines between dual literals to say, well, they are dual, they are conflicting, they're mutually exclusive, or whatever. And we just say these literals are connected, just meaning they are dual. Giving your example, I like this example, so we will see it a couple of times. Here we see we have this clause here. It's kind of an instance, a copy of this clause C2. And we have two copies here of this grayish clause here, this C1. As you can see, I just renamed it out of here. They are independent of each other. And we just draw lines between them. And lines just mean they are dual. And of course, they are dual just means there is a unifier that actually makes them dual. So we cannot just randomly draw a line somewhere. We actually also have to find a dual. And I know conjecture, this is a valid matrix proof. We will see this, we will definitely say, cool, that is the proof for this two first order clause unsatisfiable. Okay? For now, just permit me. On the next slide, I will tell you why. Namely, we call it a set of connections, respectively, just the matrix on its own, to be spanned if there is no open path. And an open path is just one literal from each clause instance that is on the matrix. So you remember, a clause instance is just something that's written vertically in the matrix. And none of these literals of this path, it's an open path if none of those literals that we put are connected themselves. So because we're logicians, we might like it if I write this way. So just what I just said. And you only care about spanning matrices, because if you don't have a spanning matrix, it's not a correct proof. And then you also define a set of connections with respect to the matrix to be fully connected. And fully connected just means each literal is connected with at least one other literal in the matrix. Okay, I know this might not be confusing, and there's a negotiation side, and so let's look at an example. In particular, this one here. It's a matrix. Cool, I wrote here my clauses vertically. So this is the first clause instance, second one, the third one. So it looks like a matrix. I drew even lines between them. Cool, but I claim this is not a valid matrix proof. And the reason for that is, well, look at these both elements here. So it's exactly one from each clause instance. And I can do an open path because none of them is mutually connected to each other. So this is not a valid first order connection calculus matrix proof. However, this is you will not be able to figure two literals in a way that will get an open path. It's just not possible. Okay. Also because I will use a lot of terminology to quickly go to them. So these are my clauses here. This I can just from each clause I can just take another instance and add it to my matrix. These are my unifiers. For every variable, eigenvariable, to be more precise, I just have a unifier that tells me to what do I want a method, can I unify it with something else? These are my clause instances, they are in the matrix. So in this case, I prove them. These are my connections, so these are just the lines connecting my literals. Of course, the matrix is basically the proof has a certain size perspective that in the series of the three clause instances in the matrix. Okay, I think now I fixed the terminology. Let's go to the interesting part, mainly about encoding this stuff here in SEC. So yeah, we discussed three different encodings. In particular, first we encoded the TABLEAUX tree, which I don't discuss here, and there might be another talk somewhere in which someone might discuss this. But for now, just focus on the connection calculus in the matrix form. In particular, we discussed two different encodings. One was a static size, that means we upfront fix the size of the matrix. And with the other one, we use a more dynamic approach in which we dynamically size the matrix based on our findings and find failing to find a matrix group. Okay, the coding idea is fairly simple. We just have two constraints. The first one is, well, we have exactly 3 clause instances in the matrix, and the other one is that this matrix is spanning. However, it turns out this is not really possible because this is not in empty. So therefore, we will use the slightly relaxed definition, which is in fact in empty, namely that the matrix contains exactly 3 clauses and that the matrix is fully connected. And as I told you before, a matrix to be fully connected just means each literal in the matrix is connected to at least something else. So this is a unique definition of them being spanning, but as it turns out, it's mostly sufficient. All right, so we just it is fully connected, but it's also spanning. So here's the workflow of the solving approach. Well, we assert there are 3 clauses to the set solver. So we assert that the matrix is fully connected. We check it for consistency of the set encoding. So is it possible to satisfy these 2 constraints? If it is, then we check if it's spanning. If it's not, well, then we go back and say, oh, there's an open path. You rule it out and say, well, not this open path, add. And then ask again for consistency. In case it's not consistent, we increment our proof outside proof size, or in case it is spanning previously, we just output the proof because it's a spanning proof, so why not? Yes. The encoding is implemented lazily. That means we don't upfront encode everything because, as you might expect, this is a huge encoding. And the unification can be very easily expressed in set solving with algebraic data type. Okay, so far this is very abstract. With more precise, we have 2 different kinds of neutrals. The first one is selector. The selector just says we have the case instance of a clause present in the matrix. So for example, in this case here, this Boolean atom just means it accepts the truth that this clause instance occurs in the matrix. Simple. And we have another Boolean atom that are called connectors that say that a certain literals that are hopefully in the matrix are also connected. And of course, the connector implicitly also implies that there is a unification constraint satisfied. But this is not a problem in set solving. There are ways to implement this. Okay. So let's look at the encoding. The encoding of there are exactly 2 clause instances in the matrix. It's fairly easy. This is a pseudo-Boolean constraint. It's mostly supported by the set solver built-in feature. For having a fully connected matrix, it doesn't look like it looks a bit intimidating, to be honest. But I have to tell you that just means if you choose a particular clause instance to be in the matrix, you have to go through all possible clauses that exist in our input clause set, take all potential clause instances of it, so all up to 3 instances of it, choose each literal out of them, and say that this clause instance is in fact also in the matrix, and that the respectively chosen clause literal instance in this clause instance is connected to the literal in our clause instance that we just assigned to in the matrix. Okay, yes, just to be clear, this is a huge content, huge difference, really huge, mostly. Okay, we just asked for these 2 constraints to be satisfied, and then for every open path we get, once we find the set solution for 1 and 2, we check is there an open path. And in case it is, we just say, well, thinking that we assign all the selectors that are currently assigned to, so in case we say clause instance 1 of certain clause C1 is selected, and clause instance 1 of clause 2 is selected, whatever. If all of them are selected, then at least one of the elements in the open path we found has to unify. Mostly this will not be possible with the set of factors. So overall, we have this decoding, and well, obviously it's sound because we just tell the set solver guess a proof. We manually check, or manually means we ask another program to check it. So definitely what we are doing is sound, because we checked it to prove the sound. So what should we do apart from being sound? It's also terminating for a fixed speed. So assuming we give a certain proof length, maximum proof length, it is terminating, and a theory says that this problem of finding such a replication is sigma to be complete. And it's only complete for a given proof size that of size speed. However, this is quite clear with exploding immediately when just implementing it, because I mean you have clauses that contain whatever 20, 30 literals. Yeah, of course, yeah, you can imagine this. This is not entirely happy with it. So therefore we came up with something we call dynamic sizing. And the idea is here that so far we assume that each clause instance can occur at most p times in our matrix. So we did not distinguish if this clause is relevant or not. We just always assume there are at most p instances of this particular clause, right? So this is a vast over approximation. Maybe we just need 2 instances of this clause, but should put our focus on another clause instance. So what we did is we used the dynamic approach, which just lazily increments this counter for each different clause. So in particular, we have here this new C. Just equals how many, just counts how many clause instances do we have at most of a certain clause. So we care about the selectors of a certain clause C up to from 1 to this new C. So in case we just assume that for a certain clause C1, we have at most 3 instances, but for another one we might have 5 different instances. So we generate only 3 Boolean atoms for the first clause, but 5 for the other one. Furthermore, for all the remaining selectors, we just assume them to be false. So assuming something to be false is a set trick just saying, we can use this atom, but we know it's false. It sounds a bit obscure, to be honest, in the first place, because why would you do that if you already know that it's false? But the point is that the set solver can learn something, a bit of information about why it failed. Can us, for example, tell us later, well, it failed because we assumed this to be false. It's not definitely it's not wrong in itself, the formula, but it is wrong given this assumption, which will be the trick, because we only increment this new C for given clause C when we have a proof attempt that failed, and the set solver told us, well, this is because we assumed a certain selector to be false. Yes, so we just base our decisions on the concept analysis and the concept problem. Again, it's very simple how we import our matrix to be fully connected. It's just the same thing as before, but for each clause instance now we only care about new C plus its respective count, the number of elements, and we just express as well. If we choose a clause, we just try to connect it to something that is already somewhere in our matrix, or we need more instead of this particular clause instance. So just to give you an example, let's assume that this group clause here, and we just have at most one clause instance of PA, and for the others we don't have any. Okay, I mean it's fine. We can have different counters for different clauses, what we actually wanted. So we just put this PA into the matrix. And we just propagate, well, given that we have 2A in the matrix, we either have to put this clause instance of this clause, the second clause here, into the matrix as well and connect it to it, or we have to add the clause instance of this one here into the matrix, because both of them could potentially unify this frequently, right? Okay, so it will fail because we assume both this to be false and this to be false, because our respective counters say so. So we get an answer for the counter. Well, it fails because this was set false and this was set to be false. Okay, well, we just increment the counter for, let's say, the second clause. Well, then it's fine, it's fine. We add this clause, okay, tells us, yeah, then you have to add either this clause instantly units connected, or this one. Well, this is still false, but it's not true, so it's fine, so we can add it. But now we have to connect this one here to something, and well, we have a similar situation now. Either we need a new instance of this clause here, because then we could unify with it or we need this one. Well, and this is now set to default. So, okay, what can we do? Well, we get an answer for it because even in the new instance of this clause 2, or we implement the counter for this clause here. Well, we can also implement this one here for the second clause again, and we can add it. But you see, this will diverge because you actually want to bump in the counter for this one here, for the third clause. So that's why we need a fair enumeration. Okay, finally, this code looks decent, I would say. However, it's entirely unsound, given that we just used it as before. In particular, this part with the exclude and open path is unsound. Well, why it's broken? Well, I think we have an example for it, but short summary, asserting now that we have at most key elements in our matrix, that we have at most the capacity of each clause in the matrix. Now breaks it because before we had that we have exactly p elements in our clause, in our matrix. So just to give an example, let's we have this for clauses, it's propositional, it's super easy, and we have here 2 attempts of proving that this is answered. The first one just doesn't use this for clause here. Well, and this is a failed approach. So immediately there's an open path, A, not B, A, so open path, not good. Whereas in the fourth, in the matrix proof down here, well, this is fine, there's no open path. Looks easy. The reason for that is, if we now propagate that, given you select those clauses here, we would propagate that, given I have assigned them true, some of them have to unify, but they definitely don't unify. This is an A and this is a Q that don't unify. The A will already not be with the A here. So actually what we're saying here is that assigning these 3 elements to true implies false. And it's not good because if it just would add another element here, this wouldn't imply false. It would be perfectly valid true. So you see, this doesn't really work. So what we have to do is, well, we just have to encode. If there's an open path, we have to choose another element that is not yet in the matrix, or we make something. We have to connect something along the open path. So in particular, we use this more complicated formula here now, which says, yeah, if you select the element, it was selected, you have to unify something on the open path, or you have to select something that is not yet in the matrix. So in particular, it means this one here. If you select those little, you have to take a new instance of either of those to the matrix. Or you have to unify something along the path, but well, this is not really possible. So, yeah. Okay. So what we did in our paper as well is to discuss some optimizations, and an obvious one is we use so many different ways of symmetry here. That can't work. And of course, if we just look at what is the difference between clause instance 3 of a certain clause and clause instance 17, and nothing. But what prevents the set from learning something about 17, but not being able to shift this somehow about shift this information somehow to 3? So that we just force the sets over to assign them in a monotonic way. If we use clause instance 3, you also have to use clause instance 2 and 1, for instance. This creates a lot of symmetries. Furthermore, we can enforce a certain term ordering as well, because again, the clause instances are exchangeable completely. So therefore, well, clause instance 1 has to be somewhat different from clause instance 2, and we cannot just swap them. So in particular, we can say, well, the substitutions have to be monotonic as well. Although we use some kind of subsumption, but subsumption and connection calculus is complicated, so we use a tiny version of it that just says if you have the same clause, you can't have it twice in the same matrix. So this is some kind of version of regularity, let's say. And we already briefly had a version of avatar-like splitting. And yeah, using a lot of different optimizations makes it even a decision procedure for the effectively propositional fragmented first order logic. Okay, Well, we implemented all this, well, just to see what happens in a prototype that used as a backend both Capital as a set backend and Set3 as an SMT backend. So using it on SMT solver or a set solver, well, let's see what happens. And we can compare against Mooncorp, which is a Rust implementation of the Mooncorp, which is kind of effective. That's standard connection calculus solver. And because we got the question quite a bunch of times, well, the complete mode of Mooncorp, of course, is already incomplete on this subs. Well, what we can see here, well, this is our encoding, this here as well, this here as well. This is the native, the one with the static size encoding. This one here is with the unsub core, the dynamically sized one. And this here is the approach using the best of both encodings. Well, I mean, as you can see, well, Mooncorp is far better. So there's nothing to, well, it's obvious. It solves more problems, has more unique problems, so yeah. So our encoding is mostly a theoretical encoding rather than a practical one, can be used for actually solving problems. Okay, yeah. One can ask, okay, what went wrong? I mean, we were thinking about really shortly, so okay, that doesn't sound good. Well, there are several things. Yep, like a 1 minute. Right. So well, we have an overhead of the set solver, pushing everything through the set solver, introduce an overhead. Okay, but okay, that's too easy. We can't always blame the set solver. It's the set solver. Well, we can blame it also in another way and say, haha, we learned stupid conflicts. But also, that's not entirely the reason. The most problematic reason is that it starts with building sub-matrices that do not make sense at all. For example, if we can say, yeah, PA is a matrix, so it's zero. But then there is a certain sub-matrix that is not connected to the first one, but it looks fine. I mean, for the set solver, it never tells me. I never tell the set solver, do this and this and this and this after that. You don't enforce a certain order, which is say, well, these are your rules, apply them somehow. And that's what's happening. You just create subgroups that do not connect to each other. In theory, they would connect eventually when it runs out of third space, but yeah, this could take quite some while. Okay, to summarize, we encoded the existence of a string metric as a set problem, which is super nice for analyzing it on a theoretical level. Also, it is nice because usually if you encode a first order problem as a set problem, you want to get it answered, and this proves that the first order theorem is answered. In this case, if we get sub, it actually tells us, cool, we have this first order group, and the model represents this first order group. We evaluated our prototype using an SCP and sub backend, but to be honest, the experiments there are rather modest. So we had an investigation of connection calculus in sub context, but the experiments are not so good because the set guidance connection calculus doesn't really work. I can tell you, and this would be a fancy animation if this would be PowerPoint, but unfortunately it's a PDF. So I can just tell you, that's not the end of the story. There is a way we can even make this efficient. And I heard that there will be someone talking about the next presentations. But for that, thank you for your attention and to the